Okay, I would like to thank you very much for the opportunity to talk about my research today. And since it's before the break and it's in the morning, I thought that maybe we can enjoy some art. And there is this series of pictures of paintings that I like very much called The Voyage of Life, which I think has described more or less what I think about ground states through my life and also a bit of the project, and maybe also will describe what you are feeling through the talk. So the first picture is called childhood. And well, here the child is coming from an unknown past. And well, it's the beginning of life. So let's start from the beginning. And I would like to make this point that a ground state is a state of minimum energy. So how does this work in quantum field theory? Well, well, in quantum field theory, well, we first I will set the setting. So we are going to talk about the ultrastatic setting. So that means that we are going to have a manifold of this product type. I'm going to have a smooth Lorentzian metric, and I'm going to focus just on the Klein-Gordon operator. So in this setting, one basically can define the ground state by its 2-point function, which is given by this expression here, which of course is a ill-defined expression as a function, but is well defined as a distribution, as a bi-distribution, and is actually the Schwarz kernel of this operator here also. And you can see that, well, the special part of the Laplacian appears there, and also the eigenvalues and all this. And in quantum field theory, in an algebraic picture, we have this linear functional and the algebra of observables. But via the GNL representation, we can see this as a Fock space and a representation of this algebra as bounded operators, and we have a special vector here. And in particular, in this case, we have a strongly one-parameter unitary group, such that its generator is positive and acts on this state in this way, which in some sense formalizes that it is the lowest energy state of the positive Hamiltonian. And this was already done rigorously in 1708 by K. But just like the childhood, too soon and too fast, it is over. And then we go to the youth. And in the youth, okay, things are less simple, but we get independence and we learn a bit new things about life. So here I would like to introduce something that maybe not many of you are familiar with, is called the Sobolev wavefront set, which basically is a mathematical tool that allows us to say in which point and in which direction some distribution has certain Sobolev regularity. And the way you do that is that you choose a point, you choose your direction, which is going to be associated with the Fourier space. Then you take a function that does not vanish at the point, and then you multiply your function with that your distribution with that function. You take the Fourier transform, you multiply it, and then you take a conical neighborhood of the Fourier space, and if that's finite, then you said it is microlocal. And if it's infinite, then it's not microlocal, and you say that it is in the Sobolev wavefront set. So here are some properties, so maybe so you can become a bit more familiar with it, a bit more comfortable with it. So basically, if you have your distribution have some certain singular support, and then you have your Sobolev wavefront set, if you project it, then that Sobolev wavefront set is contained in the singular support. The union of all the wavefront set, the closure, is equal to something called the wavefront set. So if you have heard about the wavefront set, this is how they are related. And of course, we have these examples. For example, if a function is of certain Sobolev regularity, then the Sobolev wavefront set is empty. If you take derivatives, you lose one order on the Sobolev order. And here, for example, we have two distributions. And for example, the Dirac delta is empty for s less than -1 and is positive for s bigger than 1. And basically, the wavefront set is telling us that the Dirac delta is singular at 0, 0, but in all directions. And we have another example of another distribution, which well, now we have a little bit more geometry, and it's also the way front set telling us like in which sense this is singular. And well, my talk has the name adiabatic in it. So I would like to give this definition. So basically, when we have a state, and we call it an adiabatic state of order n, if it's two-point function, it's a bidistribution that satisfies the following HS wavefront set condition. So maybe what is of this terminology? So well, the prime just basically means how you will if you have something in your wavefront set, then the prime is just telling you how it changes here, and this set C basically tells you that if you have a point and another point, something belongs to that set C if you can join them by a null geodesic, and these covectors are associated to null tangent vectors as they are parallelly propagated. And finally, DC plus basically is telling you that once you have a covector, you can use the metric to make it a vector, and you check if the first component is positive, and then if it is in C++. Okay, so that is basically what I want to say about juice. And of course, well, the last thing is that Hadamard states are the adiabatic state of infinite order, and of course the ground state is a Hadamard state, and this was shown already in the 81, but this approach using microlocal analysis is from Ratzikowski, and later on people have shown that in fact something called passivity, and with certain causal properties, you are also ground state, so this is just a bit of that. So the next painting is so far, well, at the moment is my favorite, and it's called Adulthood. And it basically reflects sometimes what I feel about the project, but also I like it very much that before the water was all smooth and it was all nice. And in this case now we have a little bit more turbulent waters. And well, I relate this with non-smoothness, which is basically what I like to talk, well, the project is about, which basically is about non-smooth spacetimes. And why am I interested in non-smooth spacetimes? Well, I think there are many good reasons. For example, basically many models of gravitational collapse have some kind of non-smoothness, in the sense of like when you like to match your fluid model with the vacuum, for example. Also, usually general relativistic fluids, when they are evolved, nonlinear dynamics enter, and shock waves are formed, and then the metric, since the right-hand side, the energy is non-smooth, the metric is non-smooth, and also there are like a lot of astrophysical models of, for example, stars with different layers of matter, which in some sense are non-smooth. At the same time, there is a question about the mathematical foundations of GR. So about the causal structure, like there is an ongoing research about to what extent one can lower the regularity and still hold what we know about the smooth case in the causal structure. And these questions about, for example, global uniqueness of Einstein's equation driven by strong cosmic censorship, which is also a question about regularity. So what's the right regularity to have well-posedness of the Einstein's equation? And in general, like existence of Einstein's equation, one usually just needs, for example, L2, which was found in the L2 curvature conjecture, which tells us that, okay, you don't need to be smooth to have a perfectly well solution of the Einstein's equations. So that's, in some sense, a motivation for non-smooth spacetimes. And in some sense, this can be seen as not strong singularities in the sense of, as Mark talked in his talk, like singularities on the Big Bang or Schwarzschild, but more like singularities that appear just because we have some physical models, and they are the easiest and more convenient way to model all these phenomena that we're trying to do. So going back to the problem, basically what I will do now is again go back to the ultrastatic setting, which is basically I will take again this metric, but the only difference now is that the metric now I will take it to be in C tau. And well, here you can see what C tau means. So if, well, C1 and C2 basically means one derivative or two derivatives, but you can also take non-integer regularity, and they are given by these norms here. So basically now the theorem, or like the thing we have proved with Elmar, all this is work with Elmar Schrohe, is that if you have a C tau ultrastatic spacetime, and here I have a condition that tau is bigger than 2, there is some, actually, we have shown it also for the case C11, but for this moment, we can also think C tau 2. If you have your 2-point function of your ground state, then we have this Sobolev condition here. So, and we have this wavefront with Sobolev wavefront set that satisfies this. So in some sense, this is what I mean by that in non-smooth static spacetimes. Of course, there exists a ground state, but our ground state will in general be non-Hadamard because we cannot go to infinite order here, but just to certain order, and that means that our ground state is an adiabatic state. For the proof of this statement, we are still like writing the last details of the paper, but we already have a paper analyzing the microlocal structure of the causal propagator, which many of the ideas can be found there. So if you're interested in the nitty-gritty, then you can look at that paper or wait like, I guess 1 month until we publish the paper with this result. So now, again, well, here is basically saying you that one can construct the 2-point function as in the smooth case. The only difference now is that, for example, these eigenfunctions are going to be non-smooth, and well, and but beyond that, then everything, in some sense, in the bidistributional sense, is the same, but in the microlocal sense, is a bit different. It's too ambitious, of course, to try to go through all the proof here, but maybe I just want to tell you like the main lemmas that are used for it. Basically, we need a lemma about the global regularity. So basically that the 2-point function is in h minus 1/2 minus epsilon. The positivity of the covariable is interesting that the regularity doesn't enter at all. So we have that for all reals. Then we have two lemmas that are somehow concerning how does this 2-point function behave away from the light cone. And here you have a bit better regularity. We have minus 1/2 minus epsilon plus tau. And then the last ingredient to then apply propagation of singularities is how those things behave at the diagonal. And here we have minus 3/2 plus tau, which is the regularity that I show you in the theorem. So here is where we lost all the regularity. And yeah, just as a kind of very brief, and well, just if someone at some point see the video later, so the tools that we use are called non-smooth differential operators. And well, basically these non-smooth differential operators, the Klein-Gordon operator is one of them. And we use something called the smoothing of symbols, which says that if you have a non-smooth differential operator, you can always divide it in a smooth differential operator and a non-smooth one. And the propagation of singularities in this case, which basically tells you that, okay, well, here is it. Yeah.
You have one more minute, okay?
Yeah, well, then, okay, so basically this is the propagation of singularities, and also like, I will also let you later if you want to see it in our paper well, and here is like a brief explanation why these numbers comes about, which basically depends on the regularity of the bidistribution. But to finish, well, we have the last, well, that's the theorem again, and we have the last painting, which is called Odd Age. And well, we have finished these turbulent waters, but also now we're seeing light, new projects, new hope. So the future works is, of course, to try to think what are the physical states in non-smooth globally hyperbolic spacetimes, and the final goal is to actually come about to answer the question, what is the minimal regularity on the spacetime metric? So one can, in the mathematical sense, have QFT plus classical spacetime, and also to think about that in the physical sense. So I think my time has run out now, so I will thank you for your attention.
Thank you, Yafet, for that such a wonderful talk. So now we have time for quick questions. So is there any question? Please raise your hand or simply unmute yourself and ask. Dan Jansen has a question. Please unmute yourself and ask the question.
Hi, Yafet. Thanks for the talk. It was very nice. I was wondering, I mean, obviously, if you want to have any kind of sensible stress energy tensor, your state needs to be regular enough. Yeah. And you mentioned, for instance, on collapse models, typically your spacetime is not smooth, but only continuous or something like that. Now, in sort of 1 + 1 dimensional models, I think it has been shown that you can still calculate the stress energy tensor on sort of well, continuous but not smooth spacetimes. But I think on 3 + 1 dimensions, this is a bit harder to show, or is not, as far as I know, not clear. What are your thoughts on this?
Yeah, I will say that, well, since global, well, we are in C2 here because we're trying to be as general as possible. Mm-hmm. And one of the main problems is that, for example, usually one uses the Hadamard condition on our states because basically tells you that all the states have the same singularity structure. So when you subtract it, you subtract equal infinity, so you get with something at the end smooth. Yeah. And this is basically also related in some sense with the geodesic flow, how you construct these Hadamard things. When you go below C11, your existence and uniqueness of geodesics becomes problematic. Mm-hmm. So even the construction is a bit strange. Nevertheless, it can be that maybe you can somehow still propagate singularities there, but then you will need somehow a substitute to say what is the universal singularity part, because you don't want that, because yeah, you can say that, okay, I have this state that has this singularity structure, but okay, but then you need maybe another state and you want to be sure that when you subtract it, they still have the same similar structure, so you can make sense of this energy momentum tensor and all this. And I think that maybe in general, it's a bit hard, but if you have maybe very detailed, for example, in these gravitational collapse models, that you know exactly how does your non-smoothness look, maybe you can, matching the geodesics or something like this, make sense of it. But yeah, at the moment, I think it's a very interesting problem, but unfortunately, I don't have a definite answer.
Yeah, I could imagine in 1 + 1 dimension, of course, you have less, let's say, directions where your geodesics can go to worry about. So that might be why in 1 + 1 it works and in 3 + 1 it may not.
Yeah, and also another point that it's that in higher and higher dimensions, somehow the fundamental solutions are more and more singular.
Yeah.
So
yeah, that's true.
Everything for this h-1/2 is for 4 dimensions. But if you fall higher and higher, then it's more and more singular. So somehow you have a more singular fundamental solution interacting with singularities from the metric. So it becomes a bit more and more messy the more dimensions you have.
And one further question I had, I don't know if there's time for this, otherwise I'll do it in the Slack. But
if it's a quick question, then I encourage you to do it now. If not, just put it in the Slack, please.
So do you know anything about the local quasi-equivalents of adiabatic states with respect, because it's known that Hadamard states are locally quasi-equivalent?
This is something we are working now on it. We have shown some properties of the ground state, like actuality and like primarity. But well, to talk about local quasi-equivalents, you need another state. So, well, we are working on that. But yeah, definitely this is something that is very interesting. And again, I'm sorry that I don't have at the moment a definite answer, but I hope I will come back to you soon.
Well, thanks.
Okay,